Aloha Physics 100 students, and welcome to your first Physics 100 video lecture. In this lecture, I'm going to be talking about how to draw free body diagrams and also how to calculate the net force on an object. So first of all, we use free body diagrams to keep track of all the forces on an object. Say I have a box and it's resting on a table. What are the forces on this object? Well, first of all, gravity is going to be pulling down. So I'll draw an arrow this way for gravity. I'll label it grav for gravity. Now, the table is also holding the box up. And this force that acts opposite gravity is usually called the normal force. And in this case, it's coming from the table. Okay, so say I'm going to push on this box. So now there is an applied force from this person who's pushing on the box, and this force is going in this direction. But there's another force acting against the applied force, and that force is going to be the force of friction. And friction will keep the box from moving quite as fast because of the applied force. So now let's draw some other free body diagrams. First, let's do the Earth and the Moon. So here we have the Earth and the Moon. And what are the forces acting on these objects? Well, the Moon has a gravitational force acting towards the Earth. And the Earth has an equal and opposite gravitational force acting toward the Moon. The Earth is pulling on the Moon, and the Moon is pulling back on the Earth. These are pretty simple because in this case, these are the only two forces that are important in this system. But if we want to start getting fancy, we can say, well, they're both being pulled on by the sun, which is over here. So this is gravity due to the sun. And maybe Jupiter's somewhere over here. But the gravity from Jupiter is pretty small compared to the gravity due to the sun and the Earth for the Moon. So that's a really small arrow. And then, maybe there's a little bit of gravity from, some nearby star or other planets around. But these forces get so small, it's not worth putting them in the diagram. Okay, so now let's take a look at another free body diagram. Here's a parachuter, and he just jumped out of the plane, and he's falling towards the Earth. He's having a great time. Here's his parachute. He's all ready to go. What are the forces acting on him? Well, first we know there's a force of gravity from the Earth that's pulling him down due to the Earth. Now there's some other gravitational forces on him, like there's probably one gravity from the sun, a little gravity from the airplane. But these gravitational forces on him are so small that we can pretty much ignore them. But there is one force acting on him that is making a difference. This is the force due to air resistance. And air resistance is a similar force to friction. As you're moving through the air, air resistance will slow you down. So it acts opposite the direction of your motion. So as the parachute diver is falling, gravity is pulling him down, but air resistance is pulling him up. And the faster and faster he goes, the harder the air resistance will work to stop him until the force of air resistance balances the force of gravity and he's no longer accelerating. And when he reaches that balance, that's something called terminal velocity. He'll still be moving very quickly towards the Earth, but his movement will not be increasing in speed because the forces are in balance. All right, so if you think about Newton's first law, it says that an object in motion tends to stay in motion with the same speed and the same direction, or an object at rest tends to stay at rest unless acted upon by an unbalanced force. So let's see if we can use free body diagrams to figure out if there are unbalanced forces and what can we predict about the motion of an object once we calculate what the unbalanced force might be. So here's a box, and here are some forces on this box. Say I have 2 newtons going down, 2 newtons going up, 5 newtons to the left, and 3 newtons to the right. Okay, so what is the net force on this box? Well, the 2 newtons up and the 2 newtons down add together to equal 0. We add these two together, 2 up, 2 down, equals 0. But I also have 5 newtons to the left and 3 newtons to the right. So I've got 5 to the left plus 3 to the right. That's going to equal 2 to the left. So my net force two newtons in this direction. So how is this object moving? Can we tell? Is it accelerating? Yes. It has to be accelerating because there is an unbalanced force on the object. Is the object moving? I'm not sure. At this instant, it could be standing still. It could be moving in this direction, in which case its speed would be increasing. It could also be moving in this direction, in which case its speed could be decreasing. If something is moving in this direction and a force is acting in the opposite direction, then you know that the velocity will be decreasing. But if you have motion in this direction, and also force in this direction, the speed increases. Okay, so let's take a look at a free body diagram for a surfer. So here we have a wave, and here's somebody riding the surfboard. There he is. He's having a good time. Okay, what are the forces acting on the surfer? Well, first of all, we always know that gravity is pulling down. So here's the force due to gravity. But he's not going down right now because the surfboard is holding him up. So there's a normal force from the surfboard pushing him up. Okay, so now the wave is pushing him forward. And are there forces pushing him back? Yes, actually. There are forces holding him back. There's drag from the surfboard and the fin down here. The surfboard in contact with the water has some friction, some drag there, and this fin pulling through the water also does. So he's not going quite as fast as he would be in a frictionless situation with just the force of the wave pushing him. So there's your free body diagram for a surfer. Okay, so let's take another example. Here's our random box. We're going to put 4 forces on this box. And these are all the same. So I've got 3 newtons acting to the left, 3 newtons to the right, 3 newtons up, and 3 newtons down. Is there a net force on this object? No, because the force in the upward direction and the force in the downward direction add to 0. The force to the left and the force to the right add to 0. There is no net force on this object. So is this object accelerating? No, it's not. It cannot be accelerating. Whatever motion it has right now, it's just going to keep that motion forever unless another force acts on it. And then the question is, how is it moving right now? I don't know. It could be at rest. It could be moving at some direction, at some speed. I don't know. But whatever it's doing, I can tell you it's going to keep doing that forever. Okay, thanks for watching. And if you have any questions, please email me at the email address that was in your syllabus. And until next time.